Okay, so we are learning how to reduce the performance drop by hazard in pipeline architecture. And then in the previous class, we learned how to handle control hazard. So you need to understand why control hazard are caused. So which means, so 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 why clock cycles are wasted by branch instructions? So it is because branch is determined late, but the branch changes, the branch instructions change PC, right? But the pipeline processor use program counter in the instruction fetch stage. So that's the problem. So actually the data hazard is the same. The in the the data hazard are also caused by the time gap. Actually the different stages in for producing the result and then using the produced result. Okay, so it's the same. Okay, sorry. Uh, the control hazard are caused by the time difference between the PC is updated by branch instruction, but this PC is used in the instruction fetch stage. So how can we reduce performance drops by this control hazard? So I explained about the causes of the control hazard, right? So in order to reduce the performance drops by control hazard, so we can determine branch instructions earlier. So I explained some the possible solution for reducing the control hazard. Okay, so I explained that. So in this, so we are learning some reduced, so simplified version of a pipeline processor. So which means, so our pipeline processor just supports BQ. Okay, so I explained that we can add the comparison unit just after the register file. So by doing this, the branch instructions can be actually the BQ. The BQ can be determined in ID stage. So the branch is determined earlier, so we can reduce the performance drops. So which means wasted cycles by control hazard. But so I also explained about the new data hazard for this solution, right? So it's because new data hazard are provoked. It is because actually this comparator is located before the data forwarding multiplexers, right? So which means we cannot use data forwarding paths in this case. So if the data dependencies are observed in the branch instructions, then the branch instruction needs to be stalled. So that was the problem. So I also explained showed some alternative solution. So which means the branch unit is located after the forwarding multiplexers, right? So these are forwarding multiplexers and then the dedicated branch unit. So the dedicated branch unit just performs subtraction, right? So using this dedicated branch unit, we can calculate the result of branch instruction earlier. But the branch, which means that, but this branch unit is in the EX stage, so which means the branch is determined in EX stage. Okay, so which means, so actually if the branch is taken, then 2 cycles are wasted. Okay, but if the branch is not taken, there is no penalty. That's what we learned in the previous class. Okay, so anyway, so we can reduce. So we can reduce the penalties by the taken branch, right? By determining the result of a branch instruction earlier. But 2 cycles are still wasted. 2 or 1 cycles are still wasted. So we can, so in order to reduce this performance drop, we can apply dynamic branch prediction. So it's the predictor. So predictor means that it just predicts the result of a branch instruction. So what is a result of a branch instruction? The result is, true or false. So there are only two cases for the branch instruction. It's a taken, branch can be taken if the condition is true, and then not taken. Branch is not taken if the branch condition is false. So there are only two cases for the result of branch instruction. And if we can predict the result of branch instruction, so this is just a prediction. So before the branch is determined, a processor can predict the result of branch instructions, right? So what is the benefit? So it's a prediction. So I said that before the branch is determined. So we can, it's just a prediction result, but we can get the result of a branch instruction earlier, right? Then, what is the benefit of this prediction? So prediction means that the benefit of a prediction means that before the result comes out, but we can just get the predicted result, and then we can execute the instructions using the predicted result. So we can execute the instructions earlier, right? So this is the benefit of a prediction. Then how can you predict the result of a branch instruction? So think about this. So that's for I equals 0, and then I is less than 100, and then I plus plus, and then some statement here. Okay, so and then so this is the for iterative loop, right? So we can implement this for iterative loop using the branch instruction. Like, so we can just check this condition at the end of this statement, like PQ here. Okay, and then we can jump to the start of this coding block. Okay, but we can just estimate the result, actually the pattern of this branch instruction, right? So this code will execute this statement repeatedly 100 times, right? So which means that once this BQ is taken, right? Is taken, then what's the next behavior? The next behavior is also taken 100 times, and then finally it is not taken. So actually in the program, so in our normal applications, we can observe the this iterative loop very frequently. Also, we can apply some say prediction to the if-else statement. So the good news is that the prediction hit rate for these branch instructions are very high in our normal applications, right? So this is the good news. I said the good news. So prediction rate is high. So around the 95%, right? Then we can apply the branch prediction technique in this case, right? So I said that using prediction, we can get the result of a branch instruction. Even though this is the predicted value, we can get the result of a branch instruction earlier, right? So using this predicted value, then we can fetch the next instruction. Then we can reduce the control hazard. So which means that we can reduce the performance drops by control hazards, right? So then how can we predict the result of a branch instruction? So if you see the the compiled instruction, then you can find many branch instructions, right? So PQ is here, and then P and E, and some instructions like add and sub, and then some other instructions, and then also the PLT, and then another PQ, not PLT, PQ here. So we can observe many branch instructions in our code. Then actually, and then we can expect that the behavior of these branch instructions are independent, right? So it means that the behavior patterns are different for different branch instructions, right? This is the branch instruction 1, 2, 3, right? But it can be dependent, right? So even though I said that, the behavior patterns of branch instructions are independent, but based on some code structure, the behavior can be dependent. But usually we can expect that the behavior of these branch instructions are independent, right? So it means, then we can apply the prediction technique for individual branch instructions, right? Because the behavior patterns of multiple branch instructions are independent. And then how can we predict the branch instruction? Then, so how can we predict the future event, the result of a future event? So we can just monitor the previous event, right? So I said that I used the four iterative loop as the example, but you can observe that if this for loop is taken, so the branch instruction for this iterative loop is taken, then it will be taken again and again. So we can just expect that, if the previous result of a branch is taken, then next result can be taken. Okay, we can just expect. It's the one example, one possible example, right? But anyway, we can predict the future event using the previous event result, right? Obviously, right? So what is required? We need to store. We need to store the result of branch instruction. So in order to monitor, in order to analyze the previous events, then we need to store, right? So which means for each branch instruction, in order to perform the branch prediction, we need to store the result, the previous result of branch instruction, like taken, not taken, taken, what, taken, not taken, like this, right? For each branch instruction. So what is required? In order to store some data, we need to have memory. And then actually this type of memory is called buffer, right? Because the value is temporarily stored. And then this is not the kind of real main memory. So it's a kind of some hardware structure. And then this type of memory is called a buffer. So using a buffer, so like this is the memory, and then we can store the result of a branch instruction, like, oh, this is the BQ, the first BQ, and then the result is the taken and not taken, taken. Oh, this is the set B and E, and then this is taken, taken, not taken, like this. And then by analyzing the previous result, we can just predict. We can predict the result of a branch instruction. So I said that for each branch instruction, we can store the result. So you know, because actually the result of a branch instruction have only two cases, like taken or not taken, then we can just store the only what bit data, right? If the branch is taken, then we can just store 1. And then if branch is not taken, then we can store 0, right? It's a bit data. So anyway, I said that so we can store the result of a branch instruction in the buffer for each branch instruction. Then how can you identify these multiple branch instructions? So identify means that, oh, we can check, oh, the current, the branch instruction is here. And then if this branch instruction is fetched like a BQ, then we need to identify this branch instruction in order to check the previous result. Then how can we identify these branch instructions? How can we identify instructions? Another question. How can we identify instructions? Instructions have its own address, right? That is program counter. So it's the same. So how can you identify data or variables? Using addresses, right? How can you identify instructions? Using program counter, because a program counter is an address of an instruction, right? So what does that mean? Using a PC, we can identify branch instruction. So for example, oh, the PC of this BQ is 0x0010. Then if the current PC is 0x0010, then we can access this entry of the buffer. And then this entry will include the previous result of branch instruction, right? Then we can read the previous result, and then based on the previous result, we can expect the the result, the current result, we can predict the result of branch instruction. That's how the branch predictor works. Okay. So, okay. So branch predictor is just a branch buffer. Okay. So that's why the branch predictor is actually called the branch prediction buffer, or BPB, right? Branch prediction buffer. So branch predictor is actually called branch prediction buffer. So it is because, as I mentioned, for each branch instruction, this BPB, the branch prediction buffer, stores the previous result, previous events of branch instructions. Okay. So I mentioned that then, so we can use program counter, but the program counter is actually for the 32-bit computer system. The bit width of the program counter is 32-bit. What's the problem? The problem is that this buffer needs to have large amount of entries, because so it's a 32-bit. So which means, so we can just access this entry of branch predictor like so PPB. So this is the kind of a branch prediction buffer, and then index. Okay, and then this I said that we can use the PC as the index of this buffer, right? Then we can just access the corresponding entry of this buffer. But what's the problem? This PC is the 32-bit. For the 32-bit computer system, right? Then how many entries are in this buffer? 2 to the power of 32. It's huge numbers, right? It's a huge number. So actually we cannot use the entire PC value. So actually for the branch prediction buffer, we use only the part of PC to identify the branch instructions. So in this case, actually the different branch instructions may have the same this index value, but it's okay because this is rare. Okay. So you can just understand that branch prediction buffer is a buffer indexed by part of PC. Okay. And then we can just store the event of branch instructions, right? And then using this event, we can predict the result of branch instruction. Okay. So let's learn about the 1-bit predictor. So 1-bit predictor means actually the 1-bit predictor. So it means in order to predict the result of a branch instruction, 1-bit predictor just uses 1 bit. Okay. So what does that mean? So I said that so we can just a single branch instruction can have only 2 cases, true or false, right? Or taken or not taken. So we can represent this result, the result of a branch instructions using bit data, right? If the branch is taken, this is 1, not taken, this is 0. So, right? So using a bit data, we can represent the result of a branch instruction. What does that mean? The 1-bit predictor. It's 1-bit predictor. So which means we just use 1 bit of data to store the previous event of branch instruction. Only one bit, right? So what does that mean? One bit predictor just stores the, the just previous event. Okay? So for example, previous event is t not taken t. And then, so this is the current branch instruction. We don't know, but one bit predictor just check the just previous event. Okay, so these results are not stored. So it one bit predictor just stores this result, this previous result, just the just previous event of the branch instructions. So it just monitors the very previous event of the branch instruction. So then how we can just calculate the prediction rate, the prediction hit rate of this one bit predictor. How? So for example, for I equals 0, and then I is less than 100, I plus plus, and then some statement, and then PQ is here. So if this PQ is taken, then it will be predicted as also taken by one bit predictor, right? If the previous event is taken, then one bit predictor just assume that the next event is also taken. If the previous event is not taken, then one bit predictor expect that the next event is also not taken. So one bit predictor just predict that the result of a branch instruction can be the same to the just previous event, right? So if the taken, then next is a taken, and then this is actually fortunately hit. So which means that, it's correct. The predicted result is also correct. And then it will be repeated 100 times. And then what is the next prediction result? And then this becomes the previous result, right? It's a taken. And then also, because the previous result is the taken, then the next is also taken. And then the prediction is correct. It's a hit. So for this iterative loop, then with the one bit predictor, the prediction rate is actually very high, right? Then how about the prediction hit rate of this nested loop? So we also use this type of loops very frequently in our normal applications, right? But we can just calculate the prediction rate of this loop. So if initially, so let us assume that the branch predictor just stores the 0, right? And then, there are two branch instructions here, right? And then I explained that a branch predictor needs to store the previous events for individual branch instructions. So which means that the branch predictor stores the previous event for this PQ, so 1, and then also the previous event for this PQ, 2. And then let us assume that the initial value is 0 and 0. So this is the BPB, and then it's a 1 and 2. Then the initial value for this branch predictor is are all zeros. Okay. Then a processor just encounters this PQ, so which means that the current PC is the PC of this PQ. Okay. This is the branch instruction. So access the BPB using this PC. Then what is the result? So what is the predicted value? So actually the previous event is 0, right? I said that initially 0. Then what is the predicted value with the 1-bit predictor? It's not taken because it's a 0 means the not taken. So it will be predicted as the not taken. It's a predicted value. But this is the first iterative loop. So it will be taken. The real value is the taken. So what that mean? This is the incorrect. It's a miss, right? And then actually this inner loop will be repeatedly executed. And then because the current result is true, is a taken, then the BPB will store the 1, right? After this branch instruction is executed. Then, oh, this is the inner loop. So it will be executed again and again. So then what is the, and then if this PQ is fetched again by this PC value, then, oh, access the BPB using this PC, then this branch predictor entry has the 1, right? So it will be predicted as the taken, the predict. And then what is the real behavior? I said that this inner loop will be taken again and again. The real value is taken. So this is hit. So so this branch instruction is predicted correctly, right? Again and again. Then how about in the last iteration? This branch instruction will be predicted as the taken, right? But actually for the last iteration, then it goes the a program will execute the next instruction, right? Because it's out of the iteration loop. So actually the real behavior is not taken. So this is the miss, right? And then the outer loop will be checked by this this entry, the entry number 2 by this PC of the branch instruction. So what is the shortcoming? So what is the disadvantage of a 1-bit predictor? So actually the inner loop, so inner loop will be repeatedly again and again, right? But for the first of the iteration of this inner loop, and then for the last iteration of the inner loop, the 1-bit predictor always miss the predicted value. So which means that the predicted result by 1-bit predictor are incorrect for the first iteration and then last iteration of this inner loop. So this is the some disadvantage. Okay. So for the inner loop, the hit rate of branch prediction can be low. Okay. So we can use the 2-bit predictor. So what does that mean? The 2-bit predictor means that we can just store we can use 2-bit of data to store the previous event of the branch instruction. So actually we can implement the 2-bit predictor using the saturated counter. So what does that mean? The counter starts from the 0, 0, 0, 1, 1, 0, 1, 1, right? But if the counter becomes 1, 1, then it is saturated. Okay, so this is the saturated counter. So if the result of branch instruction is not taken, then we just decrease the counter by 1. But it is saturated by 0, 0 in the 0, 0. And then if the taken, then we just increase the count value. But if the count value is 1, 1, 1, then it is saturated. So this is the saturated counter. It's a 2-bit counter. So this 2-bit predictor works like this. So it starts from the 0, 0, and then if the branch is taken, then it is increased by 1. So it becomes the 0, 1. And then if the branch is not taken, then it is decreased by 1. And then, but if the current value is 0, 0, and then if the not taken, then it is still 0, 0. Also, if the current value is 1, 1, then if the branch is taken, then it is still 1, 1. It's saturated. And then for this 2-bit predictor, it just actually, if the prediction value is 1, 1 and 1, 0, then we can predict the result of a branch instruction as taken. And if the value of the branch predictor is 0, 0 or 0, 1, and then the branch prediction is predicted as not taken. So using the 2-bit predictor, we can just check the two previous events. Okay. And then actually using the 2-bit predictor, we can just check some consecutive result. Okay. We just check the 2-bit, two previous result, the 2 previous event of the branch instruction. So by doing this, we can increase the hit rate of the branch prediction, branch predictor. Okay. So this is the branch predictor. So branch predictor is located in the instruction fetch stage, right? And then I said that the branch predictor is the buffer accessed by PC, right? So using the PC, then branch predictor, we can get the result of this branch predictor, and then using the previous value, we can predict the behavior of this branch instruction. So what is the benefit? We can get the predicted result of the branch instruction in the instruction fetch stage, right? So we can get, even though this is the predicted result, right? But we can get the result of a branch instruction very early. It's instruction fetch stage, right? So using the PC, also we can concurrently access the instruction memory, and then instruction is here. Okay, so this is the benefit of branch predictor. Then, but we are missing one thing. So so we can predict the result, right? But if the predicted result is taken, then what is required? We need to know the target of a branch instruction. So which means if the branch is taken, then we just calculate the target of a branch like the PC plus immediate value, and then this needs to be updated to this PC. Okay. So using the branch predictor, we can predict, even though we can know, even though this is the predicted value, we can know. We can get the result of a branch instruction in the instruction fetch stage. It's very early, right? But how about the target? Where is the target? Target is in order to calculate the target of a branch instruction, then we need to know, actually we need to get real instruction because immediate value is included in the instruction, right? So what's the problem? Oh, instruction is fetched from the instruction memory, right? And then at the late part of this clock period. So actually, we don't have enough time to get the immediate value and then calculate the target of the branch instruction, right? Do you understand? So actually, we can get the instruction in the ID stage. So what's the problem? Even though we can predict the result of a branch instruction early, so in the instruction fetch stage, but we don't know if the branch is even if the branch is taken, we don't know the target of a branch instruction. So how can you solve this issue? So if we just know the target of a branch instruction in the ID stage, then still one cycle will be wasted, even though the predicted value is correct and then taken. So how can you solve this issue? We can also store the target of branch instruction. How? So we just learned that the target of a branch instruction, target is calculated as the PC of the branch. And then we just know the PC in the instruction fetch stage. So this is okay. And then immediate value, right? Immediate value of in the branch instruction. So this immediate value is the constant, right? And then the PC value of a certain branch instruction is actually a constant, right? So actually PC is not changed. Actually, PC is the ID of the instruction. So each instruction has its own program counter value. So it means the program counter value is actually constant for a certain branch instruction, right? So what does it mean? Oh, we know PC. We know actually, but immediate value is the constant. Immediate value is in the instruction, right? Then actually target of a branch instruction is actually also constant, the constant value, which means once the branch instruction is executed, and which means once the target of a branch instruction is calculated, and we know the next target. So the target of the branch instruction actually. So which means, oh, this is the BQ, and then X1, X2, and then immediate value. And then we just predict the result of a branch instruction. Why? For the repeated branch instruction. So which means that, oh, this branch instruction will be repeatedly executed, right? Then by monitoring the previous result of this BQ, then we can predict the result. So which means branch prediction just assumes that these branch instructions will be repeatedly executed. What does that mean? Once this branch instruction is executed, oh, this is constant, also PC is constant. Oh, we can get the real target. And then this target is also constant. Do you understand? So once the branch instruction is executed, then actually we know the target of branch instruction. So, and then actually, so which means in order to use this target, we need to store. We need to store this target in the processor. So what is required? We need a buffer. What buffer? Branch target buffer. It's called the BTB, branch target buffer. So because the target of a branch instruction is constant, so once the branch instruction is executed, and then we can store this target of the branch instruction. And then after that, if the branch is repeatedly executed, then we can just use this target value. So branch target is also stored in the BTB, branch target buffer. And then this is also accessed by PC. So using the BPB, we can predict the result of a branch instruction like T or not T, taken or not taken. And then using the BTB, and then BTB is also accessed by PC, then we can get the target. And then this is the actually constant value. So then, so which means if the branch is predicted as taken by BPB, and then using this target, the PC is updated by this target from BTB. So what does it mean? Branch prediction buffer and then branch target buffer is in the instruction fetch stage. So if the prediction is correct, and then actually target is almost correct, okay, nearly 100% correct, okay. So if the branch is predicted correct, then no penalty. There is no penalty for the branch instruction by using dynamic branch predictor. So that's how the branch predictor is working in the pipeline processor. And then you can understand that using the branch predictor, we can dramatically reduce the control hazard by branch instructions, right? Right. If the branch is predicted correctly, no penalty, because we can get the result by branch prediction buffer, and we can get the target from the branch target buffer in the instruction fetch stage. Okay. So even though the modern processors use some very complex pipeline structure, a pipeline architecture. So now we are learning a very simple 5-stage pipeline architecture. But the modern processor, is also pipeline architecture, but the real structure is very, very complex. So actually the modern processors implement the out of order processing. Okay. But the modern processors also include the branch predictor, dynamic branch predictor. So in order to reduce the performance drops by the branch instructions. And then actually for the processors, the performance of this processor can be highly influenced by the performance of branch prediction buffer or branch predictor. So it's still very important, very critical for the performance of CPU. Okay, and then it is still the the CPU vendors are still working for the better branch predictors still. Okay. Okay, so we learned about the dynamic branch predictor. Okay, and then okay, I hope you can understand how the branch predictor works in the pipeline, the CPU. Okay, the last topic of the process architecture, exceptions. So, what are exceptions? Exceptions or interrupt. So in C, you can sometimes you can make a bug. Okay, so like the divided by 0, like A is some constant value, and then B is 0, and then A divided by B. Then actually this is the not a number. We cannot define the result of this divided by 0. So actually, in a computer, in a processor design, so this is the unexpected event, right? So actually the RISC-V just handle this divided by 0 in a different way, but in a classical CPU design, the divided by 0 just reports the divided by just terminates the program, and then it reports some errors. Okay, so it's kind of unexpected event in a CPU. Okay, and then actually the CPU needs to handle these unexpected events, and then these unexpected events are called the exceptions. Okay, so sometimes so you can just understand that exceptions are unexpected or very rare event. So it means that it is not frequently observed, but it is observed very rarely. Okay, and then these exceptions need to be also handled by these processors. Also, another type of exceptions is the interrupt. So when we use a computer, then we use the I/O devices like keyboard and mice, and then also our computers are connected via network devices, right? But actually, the events from keyboard or mice are very rare event. So we just think that, oh, we can type the keyboard very quickly, but actually for the processor, it's very, very slow. And then it's infrequently given, this event is infrequently given to a processor. Okay, it's a very rare event. So actually, these rare event, so it's a rare, okay, it's not frequent. These rare events are handled by software, like operating system, not hardware. Okay, because it can be handled slowly. So these rare events, so these are very rare, and then these rare events can be handled slowly. So we can use hardware for fast operation, right? But the rare event and then the slow event can be handled by software or operating systems. So these events are called interrupt. So interrupts are some events from the I/O devices. So like if we just click the mouse button, or if we just click the keyboard, then this event is given to a processor or a CPU, and CPU raises interrupt signal. Then the operating system has this interrupt handler. So it's a software, and then interrupt handler handles this event. Like if we just click the keyboard button, then the interrupt is raised in the CPU, and then the CPU calls the interrupt handler, and then the interrupt handler code is executed. Okay, so this is software. So executed means that the software code is executed by CPU, and then it returns to some point, the point of the interrupt. So this is the interrupt handling. Also, exception is the same. Exception, if the exception is detected, then the CPU detects the exceptions, right? And then the CPU calls the exception handler. Exception handler is also software. The operating system has this exception handler code, and then the CPU just call the exception handler, and then execute the instructions in this exception handler, and then returns the exception point. So I explained how the exceptions or interrupts are handled in a processor. Then this process is similar to function call, procedure call, right? Right. So I said that, oh, the exception is detected, then CPU calls exception handler, but it's a software, right? So it's just some group of instructions, right? Then it returns to the exception point. So it is similar to the function call. CPU calls using the jump instruction. CPU calls function, and then if the function is complete, and then it returns to the return point, and then this return point is stored in the array, return address, right? Actually, the operation is the same. But in order to support the exception or interrupt, the CPU actually supports some hardware components to support the exception and interrupt. But the basic operation is similar to the function call. Okay, so you can just understand this. So I mentioned that. So firstly, in order to handle exceptions, the CPU needs to detect the causes of exceptions. Okay, so which means that also the CPU reports these causes of exceptions to operating systems, right? So what is required? The CPU needs to store causes of exception or interrupt. And I said that, oh, CPU needs to return to the exception point. So which means the exception point means that the instruction that causes exception. So what is required? Return point, which means the PC of the instruction. The PC needs to be stored, and then but this is the exception. So this PC is stored in the special register, not array. So actually the array is the return address is the general purpose register. So these general purpose registers are updated by instructions, right? But exceptions are supported by hardware. Okay, so when an exception is detected, then CPU stores the causes of exception, and then PC of the instruction that causes an exception. Okay, these two data are required. So RISC-V has the SEPC. So you can find the supervisor exception program counter. Okay, it's called the SEPC, but SEPC just stores the PC of the instruction that causes an exception. Okay, this is the return point of the exception handling. And then the code as COSE, the supervisor exception cause register as COSE. So the RISC-V stores the causes of exceptions. Okay, and then jump to handler. Okay, so this is the this is how to handle exceptions. Okay, so let's see the example. So let us assume that this is the an instruction, and then the exception is detected in the EX stage. So which means that the malfunction is detected for this add operation. So this is kind of exception. Then what is required? As I mentioned, we need to store the PC of this instruction in the SEPC, and then the causes of exceptions like is stored in the S cause. Okay, and then the exception handler needs to be called. Okay, but also these operations are required. So in the pipeline architecture, so there will be multiple instructions in the pipeline stages. So for example, the add is in the EX stage, and then in the memory stage, there can be other instructions such as the sub, and then write back some other instruction like load, and then ID and instruction fetch stage. There can be some other instructions. So the CPU detected that, oh, this add, the malfunction is detected, an exception, the unexpected result, unexpected event is detected for this add instruction. So which means this add instruction has some problems, right? So it's some issues. And then these issues need to be handled. So handled by exception handler. So because there are some problems in this add instruction, the add instruction needs to be cancelled. Okay. Even so, obviously, right? So add instruction has some problems, but if add instruction is executed, then register file or memory can be updated by problematic instructions issued, right? And then we need to avoid this case. So add instruction needs to be cancelled. Then how about the previous instructions? Actually, these instructions have no problem, right? So CPU needs to complete the execution of previous instructions. So the instructions in memory stage and write back stage need to be complete. So needs to be complete. How about the next instruction? So following instructions in ID and instruction fetch. Because this instruction has a certain problem, right? Then following instructions may be influenced by this instruction. So this instruction needs to be also cancelled. So flushed. Okay. So you need to understand this. Or exception is detected. Exception is detected in a certain stage of pipeline, right? Then the instruction that causes exception needs to be flushed, so cancelled. Also, the next following instruction. Following instructions need to be flushed. But the previous instructions in the pipeline stages need to be complete. Okay. Then the CPU core exception handler. And then the exception is handled. It's processed. So, and then there can be two types of exceptions. So actually, the exception can be maybe the handled correctly, and then the program can restart from the exception point. Then if the handler is complete its operation, then it jumps to the exception point by recovering SCPC. So in this example, the PC of this add instruction is stored in the SCPC. And then after the exception is handled, then the PC has reached the PC value in the SCPC. Then what will happen? This add instruction will be executed again. But because the exception is handled properly by exception handler, then this add instruction will not make exceptions. Okay, so this is the restartable exception. But if a program cannot be recovered from an exception, then it's just terminated. The program is just terminated. So for example, divide by 0. Actually, we cannot change the result, right? So in this case, the program is just terminated, right? So there are two kinds of exceptions. So we can just recover from the exception, right? Then it is started again for the exception point. Otherwise, then terminate the program. So actually, we will learn about some virtual memory later. Actually, restartable the exception event is the page fault. Okay, so we'll learn later. Okay, that's how exceptions are handled in the pipeline architecture. So this is some hardware components that is required for supporting exception. Okay, so you can find the SCPC and then as COSE. Okay, but we can detect exceptions in any stages of a pipelining. So which means actually we can store the SCPC and S COSE in every pipeline stage. Okay. So, and then also you need to understand how the exceptions are handled, right? So I already explained like this. So this is some example code. Okay. So when an instruction causes an exception, then this instruction is cancelled, and then following instructions are also cancelled. But the previous instruction need to complete its operation. So let's see the example. Okay, we have only 3 minutes. So let us assume that this add instruction causes an exception. Okay, and then this is the handler code, right? Exception handler code. And then, you know, this is the PC of the exception handler, and then this is the PC of this code. So let's see how the exceptions are handled. So as I mentioned, the add instruction is in the EX stage, and then the exception is detected in the EX stage. And then the previous instructions are in the memory stage and write back, and then these are the next instructions. Oh, exception is detected. So the 4C, the PC of the add instruction is stored in the SEPC, and then the causes of instructions are stored in the SCOSE. And you can find that add instruction is cancelled, and then two following instructions are cancelled. It becomes the bubble. And then, but the OR instruction is in the write back stage, right? OR instruction is not cancelled. So you need to understand this. And then, this is the store instruction. What is this store instruction? This is the first instruction of the exception handler. The exception handler is called. Okay, so you can find that the exception handler is called in the instruction fetch stage. Okay, so please understand. Please try to understand how exceptions are handled. So actually, I posted the homework 3, right? The last question of homework actually is so describe this event, like how exceptions are handled. Okay, so okay, but and then the exceptions need to be handled in the order of instruction. So you need to understand, you need to remember that exceptions need to be handled in the order of instruction and not in the order of time. Okay, so I will explain later in the next class. Okay, so I will stop here and I'll see you in the next class. 감사합니다.